Hey there. In this example, we're going to solve a differential equation using a Laplace transform. In particular, this is an initial value problem, which is important for solving a Laplace solving using a Laplace transform, because you need initial conditions to make this method work. So here I have y double prime plus y equals the square root of 2 times the sine of t times the square root of 2. And my initial conditions are y of 0 equals 10 and y prime of 0 equals 0. Now, the first step in solving these problems is going to apply a Laplace transform to each part of the equation. So I'm going to take the Laplace of y double prime plus the Laplace of y equals the Laplace of root 2 times the sine of t times the square root of root 2. Okay, so the Laplace of the second derivative is going to be s squared times y of s minus s y of 0 minus y prime of 0. And that right there is why we need those initial conditions. Okay, so there's my Laplace of the second derivative, and the Laplace of y is just y of s. And now I've finished off that left side. On the right side, sine of t is going to be 2 over s squared plus 2. And so those 2's came from squaring the square root of 2. Okay, so the next step is to actually apply those initial conditions. So y of s is going to become 10, and y prime of 0 is 0. So s squared times y of s minus 10s plus y of s equals 2 over s squared plus 2. Okay, so I want to solve this for y of s, which means I'm going to add the 10s to the right side of the equation. So s squared y of s plus y of s equals 2 over s squared plus 2 plus 10s. Resist the temptation to combine the fraction with the 10s. We actually want everything to be as broken up as possible because our last step is going to be apply the inverse Laplace. And so the more this is broken down on the right side, the easier that will be. All right, so to solve for y of s, I'm going to factor the y of s out of the two terms on the left and then divide by whatever's left over. So this is y of s times s squared plus 1 equals everything on the right. And then I'll divide both terms on the right side by that s squared plus 1 to get y of s. So y of s is equal to 2 over s squared plus 2 times s squared plus 1 plus 10s over s squared plus 1. Okay, so that 10s over s squared plus 1, that's as broken down as it can be. And I can take the Laplace inverse of this already. The first fraction, however, is more work. That one has two different factors in it, and so I need to break this down into two fractions. So off to the side here, we're going to do a partial fraction decomposition on 2 over s squared plus 2 times s squared plus 1. And both of those factors in the denominator are irreducible quadratics. So when I break these up, it's going to be as plus b over the first one, s squared plus 2, plus cs plus d over s squared plus 1. Okay, it's possible that both of these have binomials, and so I need to include that in the proposed numerators. Now I'm going to multiply this equation by the common denominator of s squared plus 2 times s squared plus 1. On the left, that leaves me with just a 2. On the right, I'll have as plus b times s squared plus 1 plus cs plus d times s squared plus 2. Now, normally whenever I can, I plug in values for s to solve for these, but it's a little bit trickier with these irreducible quadratic factors. So instead, I'm going to use the traditional system of equations by first distributing everything out here. So 2 is going to be equal to as cubed plus as plus bs squared plus b plus cs cubed plus 2cs plus ds squared plus 2d. Okay, so I just distributed everything out, and now I'll gather up like terms. So I have these two s cubed terms. So a plus c has to equal 0, since there is no c cubed on the left side of this equation. I've got an s squared term for b and d, so b plus d has to equal 0, since there's no s squared termed on the left. For the s terms, I have a plus 2c, which also has to equal 0, because there's no s term. And lastly, b plus 2d equals 2, because those are the constant terms. I have to add up to the constant term on the left. So looking at these four equations, I really have two systems. I've got two equations with a and c and two equations with b and d. So I'm going to kind of treat them separately. I'm going to take this first equation and multiply it by -1. So negative a minus c equals 0. And then I'll add the other equation with a and c in it to that. So the a's cancel out, and I just get c equals 0. And well, since a plus c equals 0, that means a also equals 0. So it turns out both of my fractions do not have an s term in the numerator. Okay, so let's see what happens when we do the similar with the b and d. So let's take the b plus d equals 0, multiply that by -1. So negative b minus d equals 0. And we'll add that to b plus 2d equals 2. And now I'm going to get something non-zero. The b's cancel, I get d equals 2. And since b plus d has to equal 0, that means that b equals -2. Okay, so I didn't get everything 0. That would be a problem. I did get some non-zero numerators for each of these fractions. And I can go back to my differential equation and break this fraction up. So y of s is going to be equal to -2 over s squared plus 2 plus 2 over s squared plus 1 plus 10s over s squared plus 1. Okay, so I'm going to apply the Laplace inverse. I've gotten everything broken down. You may look at the first and second fraction here and think, oh, well, they have the same denominator. Why don't I just add those together? Well, if they had like terms in the numerator, I would absolutely do that. So for instance, if this was just a 10 and not a 10s, then I would combine those fractions. But because the terms are not like terms, I have a constant and an s term, it's better to keep them broken up for when I apply the Laplace inverse. Okay, so I take the Laplace inverse of y over s, and then the Laplace inverse -2 over s squared plus 2, plus the Laplace inverse of 2 over s squared plus 1, plus the Laplace inverse of 10s over s squared plus 1. Okay, so starting with that first one, this is a constant over s squared plus a constant squared. So this is going to be a sine function. So this is a sine of the square root of whatever's in the denominator here. So that's going to be t root 2. And then the top is also going to be a negative root 2. Gives me that coefficient of negative root 2 in the front. All right, the next one, I have a constant over s squared plus 1. So this is going to be 2 sine of t. And the last one has an s in it, so that's going to be a cosine, 10 cosine of t. And there is my answer for y of t.